The universe is a vast and mysterious place, one that continually challenges our understanding of the cosmos. We often think of space as a boundless expanse filled with stars, planets, and galaxies, each part of a grand interconnected system. However, scattered throughout the universe are regions of space that seem to defy this orderly picture. These regions are vast, empty, and mysterious, where the conventional rules of cosmic structure seem to break down. These regions are known as cosmic voids, and they represent some of the most perplexing phenomena in space. The cosmic void is not merely an empty space, but a defining feature of the universe itself, an expansive region devoid of galaxies and matter, stretching across hundreds of millions of light years. To the naked eye, these voids may appear to be nothing more than dark, empty regions between the brilliant galaxies we can observe. But the reality is far more complex and deeply fascinating. The discovery of cosmic voids has raised many questions about the fundamental nature of the universe, including its structure, evolution, and the forces that shape it. The concept of voids in space has intrigued scientists and cosmologists for decades. What exactly are these empty spaces? How did they form? And most disturbingly, could they be hiding something even more profound and mysterious, something we have yet to understand? These are just a few of the questions that arise when we begin to study the cosmic void, and they challenge us to rethink everything we know about the universe. In this chapter, we will explore the concept of the cosmic void, its significance, and why it is considered one of the most disturbing and intriguing mysteries in the universe. The vastness of the universe. Before we can dive into the concept of cosmic voids, it is important to understand the general structure of the universe. The universe is composed of an intricate web of galaxies, galaxy clusters, and superclusters, all connected by vast stretches of empty space. This structure, known as the cosmic web, is made up of large-scale filaments of galaxies, connected by vast empty regions that are often referred to as voids. In many ways, these voids form the spaces between the galactic filaments, creating a network of matter that extends across the entire observable universe. Cosmic voids are a natural consequence of the way the universe has evolved over the past 13.8 billion years. Since the Big Bang, the universe has been expanding, and this expansion has led to the formation of galaxies, stars, and clusters of galaxies. However, during this process, the matter that makes up the universe didn't spread evenly across space. Instead, it formed a complex pattern, with galaxies clustering together in vast cosmic filaments and leaving behind regions of space where little to no matter exists. These are the voids. These voids are vast regions that span anywhere from 10 to 100 million light-years across. While the space within them may appear to be completely empty, they are not entirely devoid of matter. In fact, there are still small amounts of gas and dark matter scattered throughout these regions, but compared to the densely packed areas of galaxies and clusters, the voids are virtually empty. The density of matter in these voids is much lower than in other parts of the universe, making them the largest known structures in space. The discovery of cosmic voids. The discovery of cosmic voids dates back to the early 1980s, when astronomers first noticed that the universe was not as uniformly filled with matter as previously thought. Observations made by astronomers such as Robert Kirshner and Joseph Silk revealed that large gaps existed between galaxy clusters, areas where little to no matter seemed to reside. This observation contradicted earlier models of the universe, which had assumed that matter was more evenly distributed. The term cosmic void was coined to describe these vast, seemingly empty regions of space. But as scientists began to study these voids more closely, they realized that they were far from being mere empty spaces. Instead, cosmic voids turned out to be integral components of the structure of the universe. They play a key role in shaping the distribution of galaxies and influencing the overall behavior of cosmic expansion. The voids themselves are not completely devoid of matter. In fact, they are home to very diffuse gas, dark matter, and the remnants of galaxy formation. However, compared to the densely packed areas around galaxy clusters, the voids are relatively barren. The discovery of these voids raised important questions about the nature of the universe. How could such large regions of space remain empty? And what could these voids tell us about the origins and evolution of the universe? The formation of cosmic voids. The formation of cosmic voids is tied to the large-scale processes that shape the universe. To understand how voids form, we need to examine the early universe and the process of cosmic expansion. After the Big Bang, the universe began to cool and expand rapidly. In the first few 100,000 years, the universe was filled with a hot, dense plasma of particles. As the universe continued to expand, it began to cool, allowing atoms to form and matter to clump together due to gravitational attraction. Over time, these clumps of matter formed the first galaxies and stars. However, the process was not uniform. Some areas of space had a higher concentration of matter, while others had much less. As matter clumped together to form galaxies, the regions with lower matter density began to form voids. These voids expanded as the universe continued to grow, with gravity pulling matter into the denser areas, leaving vast regions of space relatively empty. The formation of voids is also influenced by the expansion of the universe itself. The universe has been expanding since the Big Bang, and this expansion has caused the matter within it to spread out. Over time, the gravitational pull of galaxy clusters has created an even more pronounced structure, with filaments of galaxies connected by enormous voids. These voids are a natural outcome of the universe's ongoing expansion and the way in which matter has clumped together over billions of years. The structure and size of cosmic voids. Cosmic voids vary greatly in size. Some are small and localized, while others are enormous, spanning hundreds of millions of light-years across. The largest voids, such as the Hercules Corona Borealis Great Wall, are so vast that they contain few or no galaxies at all. This supervoid is one of the largest known structures in the universe, and its sheer size challenges our understanding of cosmic structure. To give an idea of its scale, it is so large that it could fit thousands of Milky Way-sized galaxies within it, yet it remains largely empty. The sizes and shapes of cosmic voids are not uniform. While some voids are spherical, others are more irregular in shape, stretching across vast swaths of the universe. They are often described as being like bubbles in a cosmic foam, with galaxies and matter concentrated in the filaments between them. The voids themselves may be sparsely populated with small galaxies, stars, and gas, but overall, they are remarkably empty compared to the densely packed clusters of galaxies we find elsewhere in the universe. Interestingly, cosmic voids have been observed to influence the movement of galaxies. The gravitational pull of the surrounding matter in the filaments causes galaxies within the voids to move differently from those outside of them. This dynamic behavior suggests that voids are not just empty spaces, they play an important role in shaping the behavior of galaxies and the overall expansion of the universe. The disturbing nature of the void. At first glance, cosmic voids may seem like nothing more than large regions of empty space, seemingly benign and unremarkable. But it is this very emptiness that makes them so disturbing. The fact that these regions exist as vast, nearly empty expanses in the otherwise dense universe raises questions about the nature of space itself. How could such enormous regions of space remain void of matter for so long? And what does this tell us about the structure of the universe? The existence of these voids forces us to confront the fact that the universe is not as orderly and uniform as we once thought. There are large-scale patterns of matter and voids that make up the very fabric of the cosmos. But these voids, places where matter is conspicuously absent, are not just empty gaps. They are an integral part of the universe's structure, and their existence challenges our fundamental understanding of cosmic organization. Moreover, the size and scale of these voids seem to defy our expectations of how the universe should be structured. How can such enormous regions remain devoid of matter when everything in the universe appears to be in motion, constantly interacting under the influence of gravity? Is there something fundamental about the nature of these voids that we have yet to understand? These are questions that continue to puzzle scientists, and they are part of the reason why cosmic voids are considered one of the most disturbing mysteries in space. The mystery of the void. What could be hiding? One of the most unsettling aspects of the cosmic void is the possibility that these empty regions may be hiding something more profound, something that we have yet to discover. Could the voids be evidence of something unknown, something beyond the scope of current scientific understanding? Some scientists speculate that voids may contain hidden structures or phenomena that we have not yet been able to detect. These could be related to dark matter, unknown cosmic objects, or even aspects of space-time itself that are still a mystery. Could the voids be an indication of something larger, an unknown force or dimension that is affecting the structure of the universe? As we continue to study these mysterious regions, new theories and ideas are emerging that may help us understand their true nature. What lies behind the void, and what secrets does it hold? These are questions that will likely continue to challenge and intrigue scientists for years to come. To understand the mystery of the cosmic void, we must first comprehend the large-scale structure of the universe itself. The universe is not a simple uniform expanse of matter, but a complex and dynamic network of galaxies, galaxy clusters, and vast voids. These structures are intricately interwoven, forming a cosmic web that stretches across unimaginable distances, with matter organized into filaments, knots, and vast empty spaces between. The discovery of the cosmic void and its role within this vast cosmic framework challenges our previous conceptions of the universe, urging us to rethink its organization and the forces that shape it. In this chapter, we will explore the structure of the universe, starting from the smallest components to the largest observable scales. By understanding how galaxies and clusters of galaxies are distributed and how these large-scale structures are formed, we can begin to appreciate why the cosmic voids exist and what they might reveal about the nature of space and the universe itself. The cosmic web, galaxies and clusters. The universe, as we know it, is made up of galaxies, vast collections of stars, gas, dust, and dark matter. These galaxies are not scattered randomly across space, but rather form large structures known as galaxy clusters. Clusters of galaxies are held together by gravity, and these collections of galaxies often contain hundreds or even thousands of individual galaxies. The largest of these clusters are called superclusters, and they are the largest known structures in the universe. The distribution of galaxies and clusters is not uniform. Instead, they are organized into a vast interconnected web of filaments and voids, a structure that astronomers refer to as the cosmic web. This web is made up of vast strands of galaxies and clusters that are connected by filaments of dark matter, which is invisible but detectable through its gravitational effects on visible matter. The filaments form the spines of the web, and the spaces in between these filaments are filled with massive voids. The cosmic web is an awe-inspiring structure that spans the entire observable universe. The vast majority of the universe's visible matter is concentrated in these filaments, with the voids acting as the gaps between the galaxies. The study of the cosmic web has revealed a great deal about the large-scale structure of the universe, showing how galaxies cluster together and how dark matter influences the distribution of matter. The cosmic web is not static. It is constantly evolving as galaxies move, collide, and interact with each other. The voids, in this sense, are as important as the filaments. They represent the spaces where galaxies are sparse or absent, and they play a crucial role in the overall structure of the universe. Galaxy clusters and superclusters. The largest concentrations of galaxies are found in clusters. These galaxy clusters are massive, gravitationally bound systems that can contain hundreds to thousands of galaxies. The Milky Way is part of a small galaxy group known as the Local Group, which includes the Andromeda Galaxy and about 50 other smaller galaxies. On a larger scale, the Local Group is part of the Virgo cluster, which itself is part of the much larger Laniakea supercluster. Galaxy clusters form the knots of the cosmic web, where galaxies and other forms of matter are packed tightly together. These clusters are typically surrounded by vast voids, regions of space where galaxies are almost entirely absent. Understanding the behavior of galaxy clusters and their interactions is essential for studying the formation and evolution of the universe. For example, galaxy clusters often exhibit phenomena like gravitational lensing, where the gravitational pull of massive clusters distorts the light from more distant objects behind them. This effect provides crucial insights into the distribution of dark matter in the universe, as dark matter makes up the bulk of the mass in galaxy clusters. Superclusters, the largest structures in the universe, are massive groupings of galaxy clusters and other matter. The Laniakea supercluster, where the Milky Way resides, spans over 500 million light-years and contains thousands of galaxies. Understanding the dynamics of superclusters can help scientists study the forces that shape the evolution of large-scale structures and the ways in which gravity and dark matter influence their formation. Despite their vastness, galaxy clusters and superclusters are only a small part of the larger cosmic picture. Surrounding these massive concentrations of galaxies are the enormous empty spaces we call cosmic voids, regions that are vastly less dense in matter and devoid of the galactic structures found in other parts of the universe. These voids, as we will explore, are just as crucial to our understanding of the universe as the galaxy clusters and superclusters they surround. Cosmic voids, the empty spaces between galaxies. Cosmic voids are vast regions of space that contain relatively little matter compared to the surrounding filaments of galaxies and clusters. Voids can be anywhere from tens of millions to hundreds of millions of light-years in diameter, making them the largest known structures in the universe. Though they are often described as empty space, they are not truly devoid of all matter. Instead, they are characterized by very low densities of galaxies, stars, and other matter. These voids were first identified in the early 1980s when astronomers noticed large regions of space where galaxies seemed to be absent. The discovery of cosmic voids fundamentally changed our understanding of the universe's structure. Before the identification of voids, it was assumed that galaxies were evenly distributed across the universe. The realization that voids exist challenged this assumption and led to new theories about the evolution of the cosmos. Despite their name, voids are not completely empty. They contain diffuse gas and dark matter, which are spread thinly across the void. There may also be a few isolated galaxies or dwarf galaxy groups scattered throughout the void, but the overall density is much lower than in the surrounding cosmic filaments. These voids are regions of relative emptiness, and the stars and galaxies within them are often spread far apart. How do voids affect the universe? The presence of voids in the universe is not just a matter of empty space. They have profound effects on the dynamics and behavior of galaxies and clusters. Voids influence the motion of galaxies, causing them to move more slowly and have different velocities than galaxies in denser regions. This effect is known as the cosmic flow, and it describes how galaxies move through the expanding universe in response to the gravitational pull of surrounding galaxy clusters and filaments. The study of voids and cosmic flows provides valuable insights into the large-scale structure of the universe and how galaxies are distributed across space. Voids also provide an excellent environment for studying the cosmic microwave background, CMB, the faint afterglow of the Big Bang. The CMB is a crucial piece of evidence for understanding the early universe and its evolution. Because voids are relatively free of dense matter, they provide a clearer view of the CMB, allowing scientists to study the fluctuations in the cosmic background radiation more accurately. This research can shed light on the conditions that existed in the universe's infancy and help scientists refine models of cosmic evolution. Dark matter and dark energy in the cosmic web. In addition to galaxies, the large-scale structure of the universe is shaped by two mysterious and unseen components: dark matter and dark energy. Dark matter makes up about 27% of the universe's total mass and is believed to be responsible for the gravitational effects that hold galaxies and galaxy clusters together. It interacts with normal matter only through gravity, and it does not emit or absorb light, making it invisible to traditional telescopes. Dark matter is thought to be concentrated in the filaments of the cosmic web, where it helps form the dense regions of galaxy clusters and superclusters. Dark energy, on the other hand, makes up about 68% of the universe's total energy density. It is thought to be responsible for the accelerated expansion of the universe. While dark matter is associated with the gravitational pull that brings matter together, dark energy exerts a repulsive force that pushes galaxies apart. The interplay between dark matter and dark energy is crucial for understanding the expansion of the universe and the structure of cosmic voids. In fact, voids may be the product of the combined action of dark matter and dark energy, with dark matter pulling matter into filaments and dark energy pushing the regions in between apart. Voids and cosmic evolution. Cosmic voids also provide valuable insights into the overall evolution of the universe. Voids are the product of the expansion of the universe and the uneven distribution of matter. As the universe continues to expand, the voids grow larger, and their influence on the motion of galaxies becomes more pronounced. Understanding the formation and growth of voids is essential for understanding the history of the universe and how it has evolved over time. The study of voids also helps scientists refine models of galaxy formation. Voids are regions where galaxies are scarce, and studying how galaxies move in and out of voids can reveal how galaxies form, interact, and evolve over cosmic timescales. It is thought that galaxies formed in the denser regions of the universe and were then distributed by the gravitational pull of the cosmic web. Voids are areas where galaxies have not yet formed or have been swept away, and understanding their development can provide valuable clues about the early universe. The search for hidden structures in the voids. The cosmic voids are not truly empty. Rather, they are sparsely populated regions that are home to a variety of cosmic phenomena. While we have a good understanding of the overall structure of voids, much remains unknown about the specific objects and forces that reside within them. Could there be hidden structures, unknown phenomena, or even dark matter concentrated in the voids, waiting to be discovered? As we continue to observe the voids and refine our models of cosmic evolution, it is likely that we will uncover new, surprising features that challenge our understanding of the universe. Whether these features are linked to dark matter, dark energy, or unknown cosmic objects, the study of cosmic voids remains one of the most exciting and unexplored areas of modern cosmology. To fully appreciate the significance of the recent discovery in the Milky Way and the broader mysteries of the universe, it's essential to understand the nature of cosmic voids, vast, nearly empty regions of space that occupy a significant portion of the cosmos. Though these voids may initially seem like mere gaps in the fabric of the universe, they are far more complex and enigmatic than their emptiness suggests. The study of voids has become a key area of interest in cosmology, as these seemingly empty spaces can reveal much about the underlying structure of the universe, the forces that shape it, and the history of cosmic evolution. In this chapter, we will delve into what cosmic voids are, how they form, and why they are considered such important features of the universe. We'll also explore the role they play in shaping the cosmic web and their impact on the distribution of galaxies and dark matter. Though these voids may seem at first like insignificant regions, their study can offer insights into the fundamental laws that govern the universe and the forces that shape its evolution. The definition of cosmic voids. At its core, a cosmic void is a vast region of space that is largely devoid of galaxies, stars, and other forms of visible matter. These voids are not entirely empty. Rather, they have a much lower density of matter compared to the surrounding cosmic structures. While the universe is filled with galaxies, clusters of galaxies, and superclusters, voids represent the vast, relatively empty spaces between these dense regions. These voids can span millions of light years across, and they are the largest known structures in the universe, making up about 80% of the volume of the cosmos. Cosmic voids are typically defined by their low galaxy density, but they are not completely devoid of matter. Within a void, There may still be small amounts of gas, dark matter, and even a few isolated galaxies or dwarf galaxy groups. However, the overall density in these regions is far lower than in the surrounding areas of the universe, where galaxies and clusters of galaxies are abundant. These voids are characterized by their emptiness. There are vast stretches of space where the gravitational pull from surrounding structures has left them nearly devoid of galaxies. The key feature of cosmic voids is their relative emptiness, which contrasts sharply with the highly dense and clustered regions where galaxies and clusters of galaxies form. This stark difference in density gives voids their unique properties and makes them an important subject of study for cosmologists. By understanding how voids form and how they interact with the surrounding matter, scientists can gain valuable insights into the nature of the universe itself. How do voids form? The formation of cosmic voids is a result of the large-scale processes that govern the universe's evolution. To understand how these voids come into being, we must first look at the way the universe has evolved since the Big Bang. In the early universe, matter was distributed more uniformly. However, due to small fluctuations in the density of matter, gravity began to pull matter together, causing clumps of gas and dust to form. Over time, these clumps grew into the first galaxies, which continued to attract more matter, eventually forming clusters of galaxies and superclusters. As galaxies and clusters formed, the areas between them became increasingly empty, and the voids began to take shape. Cosmic voids are, in essence, the empty spaces between these cosmic structures. As gravity pulled matter into filaments and clusters, it left behind vast regions of low-density space. The regions with the lowest density of matter grew into the voids we observe today. These voids are the natural outcome of the universe's expansion, as matter clumps together in some regions while being stretched apart in others. It's important to note that cosmic voids are not just random gaps in space. They are a fundamental part of the large-scale structure of the universe. The cosmic web, the intricate network of galaxies and clusters, is made up of dense regions of galaxies connected by the voids in between. These voids are just as crucial to the universe's structure as the galaxies themselves, and they play a significant role in shaping the behavior of the cosmos on the largest scales. The size and scale of cosmic voids. Cosmic voids are the largest known structures in the universe, often spanning hundreds of millions of light-years across. While individual voids can vary in size, many of the largest voids are vast and contain very few galaxies or stars. Some of the most massive voids in the universe, such as the Hercules Corona Borealis Great Void, are so enormous that they dwarf entire galaxy clusters. The Hercules Corona Borealis Great Void, for example, is a region of space that stretches over 1 billion light-years and contains very few galaxies within its vast expanse. While these supervoids are some of the largest known structures in the universe, there are also smaller voids scattered throughout the cosmic web. Some voids are only tens of millions of light-years in diameter, while others can stretch for hundreds of millions of light-years. Despite the size of these voids, they remain largely invisible to the naked eye and are only detectable through the study of the distribution of galaxies and other cosmic matter. The sheer scale of these voids is mind-boggling. For context, the Milky Way galaxy is about 100,000 light-years across, and the distances between the galaxies and the voids are often many times greater. To put this in perspective, the average distance between galaxies in the Milky Way's local group is roughly 1 million light-years, while the distances between galaxies in the larger voids can exceed 100 million light-years. This vast emptiness creates an environment where gravity is weaker and the movement of galaxies within the void is more sluggish compared to the densely packed regions of the universe. Voids in the cosmic web. Cosmic voids are an integral part of the cosmic web, the large-scale structure of the universe that consists of galaxies, clusters of galaxies, and the vast empty spaces between them. The cosmic web is often described as a foam-like structure, with galaxies and clusters forming the bubbles and voids representing the gaps in between. These voids are not random, but rather They are organized into a pattern that reflects the larger structure of the universe. The voids in the cosmic web are not uniformly distributed. They are shaped by the gravitational pull of galaxies and clusters. The galaxies tend to cluster together in filaments and walls, while the voids are the vast spaces in between. This network of galaxies and voids forms a complex web-like structure that stretches across the entire observable universe. The cosmic web is the largest scale structure in the universe, and the voids within it are crucial for understanding the behavior of matter on these vast scales. Voids are also dynamic structures. As the universe continues to expand, the voids grow larger, and the galaxies and clusters at the edges of the voids move further apart. This expansion has been driven by dark energy, a mysterious force that is causing the accelerated expansion of the universe. The relationship between voids, galaxies, and dark energy is still not fully understood, but studying these large-scale structures can provide valuable insights into the fundamental forces that drive the evolution of the universe. The role of voids in cosmic evolution. Voids play a key role in the evolution of the universe. As the universe expands, the voids grow larger, and the galaxies within them continue to move further apart. This process of cosmic expansion is driven by the force of dark energy, which is responsible for the accelerated expansion of the universe. As dark energy pushes galaxies apart, the voids continue to grow, creating even larger gaps between galaxies and clusters. The study of voids is important for understanding the overall structure and evolution of the universe. By analyzing the size, distribution, and behavior of voids, scientists can gain insights into the forces that shape the universe's structure and the processes that continue to drive its expansion. Voids also provide a unique opportunity to study the effects of dark matter and dark energy, two of the most mysterious components of the universe. By examining the way galaxies move in and around voids, scientists can refine their models of how dark matter and dark energy influence the formation and evolution of cosmic structures. The influence of voids on galaxies and clusters. Voids don't just shape the structure of the universe. They also influence the behavior of galaxies and clusters. The gravitational effects of the surrounding filaments of galaxies cause galaxies and voids to move differently from those in denser regions of the universe. This phenomenon is known as cosmic flow. Galaxies within voids are often found to move more slowly and exhibit different velocities than those in the surrounding structures. These motions are a key area of study for astronomers, as they provide insights into the distribution of dark matter and the forces that govern the motion of galaxies. The influence of voids on galaxies also extends to their formation and evolution. It is thought that galaxies formed in the dense regions of the universe, where gravity pulled matter together to create stars and clusters. Over time, galaxies moved into the voids as the universe expanded, and the distribution of galaxies across the cosmic web became more pronounced. Studying how galaxies evolve in the voids can provide valuable clues about the early stages of galaxy formation and the factors that influence the development of galactic structures. The surprising role of voids in star formation. One of the most surprising discoveries in recent years is that cosmic voids may not be as devoid of activity as once thought. While voids are generally seen as regions where galaxies and stars are scarce, some research has suggested that star formation can still occur in these seemingly empty spaces. Recent observations have revealed that some voids are home to small, isolated galaxies that are still forming stars. These star-forming galaxies, though rare, challenge the idea that voids are completely inactive regions of space. In fact, some astronomers believe that voids may play an important role in the formation of certain types of galaxies. These void galaxies may be isolated from the influence of larger, more massive structures, allowing them to evolve in unique ways. The study of star formation in void galaxies is an exciting area of research, as it could provide new insights into the processes that govern galaxy formation and evolution. voids, and the mysteries of dark energy. Finally, cosmic voids may hold the key to understanding dark energy, the mysterious force that is causing the accelerated expansion of the universe. Dark energy is thought to be responsible for the ever-increasing speed at which galaxies are moving apart, and it is believed to make up about 68% of the total energy content of the universe. While dark energy's effects are felt on the largest scales, its influence on the voids is particularly pronounced. The expansion of the voids driven by dark energy provides valuable clues about the nature of this enigmatic force. By studying the relationship between dark energy and the growth of voids, scientists can learn more about the fundamental properties of dark energy and its role in the evolution of the universe. The study of voids, therefore, is not just about understanding empty space. It is a window into some of the deepest mysteries of cosmology and the forces that govern the cosmos. The discovery of cosmic voids marked a pivotal moment in our understanding of the universe. For centuries, astronomers and cosmologists believed the universe to be a more uniform structure, with galaxies scattered evenly throughout space. However, the identification of vast empty regions, what we now refer to as cosmic voids, shattered this long-held assumption. These voids revealed a deeper, more complex cosmic web, one that intertwined galaxies and galaxy clusters with vast expanses of emptiness that we had previously overlooked. In this chapter, we will explore the history of the discovery of cosmic voids, the technologies and methods that led to their identification, and the implications this finding has had on the way we view the universe. The study of voids not only challenged established ideas about the universe's structure, but also opened up entirely new areas of research that continue to shape our understanding of the cosmos today. The early understanding of the universe's structure. Before the discovery of cosmic voids, scientists and astronomers had a relatively simple view of the universe. They believed that matter was distributed more or less evenly throughout space, with galaxies, stars, and other cosmic objects spread out across the cosmos in a relatively uniform pattern. This idea of a homogeneous universe was based on the assumption that gravity would naturally pull matter together, creating a more even distribution of galaxies over time. The idea of voids, large empty regions of space with very few galaxies, was inconceivable. Without the technology and methods to observe distant parts of the universe with high precision, astronomers believed that the universe was mostly filled with matter. However, as technology advanced and astronomers began to observe deeper and farther into space, this belief was soon overturned. The discovery of voids. Pioneering observations. The breakthrough in the discovery of cosmic voids came in the early 1980s, when astronomers began to notice something unusual in the large-scale structure of the universe. Using data from galaxy surveys and advanced telescopes, scientists began mapping the distribution of galaxies across the universe. In doing so, they noticed vast regions where very few galaxies were present, regions that were much more sparsely populated than the surrounding areas. One of the first significant findings came from the study of the Southern Sky Redshift Survey in 1982. The data collected from this survey revealed large gaps between galaxy clusters, and it was here that scientists first observed the existence of vast empty regions. These gaps were far larger than any voids previously imagined, and they challenged the notion that galaxies were distributed evenly across space. It became clear that the universe was far more complex than anyone had anticipated. In the years that followed, additional surveys and observational data from other projects, such as the CFA Redshift Survey in the late 1980s and early 1990s, helped to solidify the idea of cosmic voids. The CFA survey, in particular, provided a large dataset of galaxy positions and redshifts, the measurement of the stretching of light waves due to the expansion of the universe, revealing even more voids and helping astronomers map the structure of the universe with greater precision. The detection of voids was made possible by the ability to observe galaxies at greater distances and with greater accuracy. By measuring the redshifts of distant galaxies, astronomers could determine their velocity and their distance from Earth. This, in turn, allowed them to map the structure of the universe and identify the regions of space where galaxies were sparse. The role of technology in the discovery. The detection of cosmic voids would not have been possible without the advancements in astronomical technology that took place in the latter half of the 20th century. The development of large-scale galaxy surveys and the ability to observe galaxies at great distances played a crucial role in the identification of voids. Prior to these advancements, astronomers had a limited view of the universe, and many of the vast empty regions were invisible to them. One of the most important technological advancements was the development of radio telescopes and optical telescopes capable of observing galaxies far beyond the reach of the human eye. The Hubble Space Telescope, launched in 1990, revolutionized our ability to observe distant galaxies with unprecedented clarity, providing high-resolution images of deep space and allowing astronomers to identify voids and other cosmic structures with greater precision. Additionally, computer simulations played a crucial role in modeling the large-scale structure of the universe. By simulating the behavior of galaxies and their interactions over billions of years, scientists could test their hypotheses about how voids form and how they fit into the broader cosmic structure. These simulations also allowed astronomers to predict the existence of voids and to refine their observational strategies to better detect them. Advancements in gravitational wave detection and radio wave astronomy also contributed to the discovery and study of voids. These tools provided new ways of observing distant regions of space that would have otherwise remained hidden. Gravitational waves, for example, can reveal the presence of massive objects like black holes or neutron stars, even in areas where light cannot travel, further contributing to our understanding of the voids and their role in the universe. The role of surveys in mapping voids. The discovery of cosmic voids was largely driven by galaxy surveys, systematic surveys that catalog the positions and redshifts of galaxies across large areas of the sky. The first major survey, the Zwicky survey in the 1950s, began to catalog galaxies and their redshifts, but it wasn't until the 1980s that these surveys began to uncover the voids in the universe. The 2DF Galaxy Redshift Survey, which was completed in the early 2000s, provided even more detailed data on the large-scale structure of the universe. It revealed a web-like pattern of galaxies and voids stretching across vast distances. One of the significant contributions of this survey was the identification of supervoids, enormous voids that could span hundreds of millions of light years. These supervoids were far larger than anything previously imagined and represented an entirely new scale in the study of the cosmos. Perhaps the most significant development in the study of voids came with the Sloan Digital Sky Survey, SDSS, which began in 2000. The SDSS produced a detailed three-dimensional map of the universe, cataloging the positions and redshifts of millions of galaxies. This survey revealed a vast network of voids scattered across the sky, confirming that these empty spaces were not just local phenomena, but a fundamental feature of the universe's structure. By studying the SDSS data, astronomers could not only detect the voids themselves, but also measure their size, shape, and distribution within the cosmic web. What the discovery of voids reveals about the universe. The discovery of cosmic voids forced astronomers to rethink the way they understood the universe. Prior to this finding, scientists had assumed that matter was distributed relatively evenly across space. The realization that the universe contains these enormous gaps between the cosmic filaments of galaxies and clusters suggested that the structure of the universe was far more complex than previously thought. The existence of cosmic voids also provided strong evidence for the large-scale expansion of the universe. The voids are the result of the stretching of space itself, a process that has been happening since the Big Bang. As the universe expands, matter is pulled into the dense regions of filaments, leaving behind the vast empty spaces known as voids. This process is still ongoing, and the voids continue to grow as the universe expands at an accelerating rate. Furthermore, The study of cosmic voids has led to a deeper understanding of dark matter and dark energy, two of the most mysterious components of the universe. Dark matter, which is thought to make up about 27% of the universe's mass, plays a crucial role in the formation and structure of galaxies and clusters. Dark energy, which is responsible for the accelerated expansion of the universe, has a direct impact on the growth of voids. The relationship between these two forces is still a topic of intense study, and the discovery of voids has provided valuable insights into how they interact. Voids as a window into the early universe. One of the most exciting aspects of the discovery of cosmic voids is their potential to offer a glimpse into the early universe. Because voids are areas with low density, they are often less affected by the gravitational forces that shape the rest of the universe. This allows scientists to study the primordial conditions of the universe, untouched by the processes of galaxy formation and star formation that have shaped much of the cosmos. By studying the distribution and evolution of voids, scientists can learn more about the early stages of the universe just after the Big Bang. They can study how matter was distributed and how the cosmic web began to form. The voids may also provide insights into the behavior of dark matter and dark energy during the universe's infancy, giving us a clearer picture of the forces that drove its early expansion. The future of void research. While much has been learned about cosmic voids since their discovery, there is still much to explore. New telescopes, space missions, and surveys will continue to reveal more about these vast, empty regions of space. The upcoming James Webb Space Telescope and Square Kilometer Array are expected to provide even more detailed data on the voids, allowing scientists to study them with unprecedented precision. Future research will focus on understanding the role of voids in the overall evolution of the universe, including how they affect the motion of galaxies, the formation of cosmic structures, and the growth of dark matter and dark energy. As our understanding of these mysterious regions deepens, we may uncover even more surprising insights into the fundamental nature of the universe. The discovery of cosmic voids has led to a cascade of new questions about the structure and behavior of the universe. What are these vast, empty regions, and how do they fit into the larger cosmic framework? While voids were once viewed simply as areas devoid of matter, their existence has prompted numerous scientific hypotheses and theories. These ideas aim to explain not only how voids form, but also what they reveal about the fundamental forces at work in the universe. In this chapter, we will explore the leading theories behind the formation of cosmic voids, as well as their implications for our understanding of the universe. Voids as a natural consequence of cosmic expansion. The most widely accepted explanation for the formation of cosmic voids is that they are a natural consequence of the expansion of the universe. Since the Big Bang, the universe has been expanding, causing galaxies to move farther apart over time. This expansion has led to a sort of cosmic stretching of space itself, creating regions where matter is sparse and galaxies are spread thinly across vast distances. In the early universe, matter was distributed more evenly, but as the universe expanded, slight fluctuations in the density of matter began to grow. Areas with slightly higher density of matter formed the galaxies, while areas with lower density formed the voids. These voids represent the large, empty spaces between the cosmic filaments, the massive structures that form the skeleton of the universe. As the universe continued to expand, the voids grew larger, and their influence on the motion of galaxies became more pronounced. This theory, based on the principles of cosmological inflation and the Big Bang model, suggests that voids are a natural feature of the universe's evolution. As matter accumulates in the dense regions of filaments, the empty spaces between them become even more pronounced. The ongoing expansion of the universe, driven by the force of dark energy, continues to stretch these voids, making them larger over time. This process of cosmic expansion is an ongoing one, with voids continuing to grow as the universe ages. The role of gravity and dark matter in void formation. While the expansion of the universe provides a broad explanation for the creation of cosmic voids, Gravity and dark matter also play crucial roles in shaping these voids. In regions where the density of matter is slightly higher, gravity pulls matter together to form galaxies, stars, and clusters. This gravitational pull is responsible for the formation of the dense filaments of galaxies that stretch across the universe. On the other hand, areas with lower matter density are not subjected to the same gravitational forces. In these regions, matter is more sparse and gravity has less of an influence. Over time, the lack of gravitational pull in these areas allows the voids to expand as matter is drawn toward the denser regions. This interaction between gravitational forces and the distribution of matter is what shapes the structure of the cosmic web and the formation of voids. Dark matter is an essential component in this process. While it cannot be directly observed, dark matter makes up a significant portion of the mass in the universe and exerts a gravitational pull on visible matter. Dark matter does not interact with light, so it is invisible to telescopes, but its presence is inferred from its gravitational effects. It is believed that dark matter is responsible for holding galaxies and galaxy clusters together, and that its distribution plays a crucial role in the formation of voids. Dark matter is thought to be concentrated in the filaments of the cosmic web, with voids being regions where dark matter is less abundant. The gravitational effects of dark matter in these dense filaments pull galaxies toward one another, leaving the voids as regions of relative emptiness. This is why voids are often observed to be free from large-scale matter and galaxy clusters. They are, in essence, areas where dark matter and visible matter are less concentrated, leading to lower galaxy density. Voids is the result of large-scale structure. Formation. Another theory proposes that voids are a result of large-scale structure formation in the universe. According to this idea, the distribution of galaxies and clusters across the universe is not entirely random, but rather follows a pattern that has been shaped by cosmic forces over billions of years. The cosmic web, with its filaments of galaxies and vast empty voids, is the result of the way that matter clumped together under the influence of gravity. In the early universe, matter was spread relatively evenly across space, but as gravity began to pull matter together, denser regions formed the first galaxies and clusters. As galaxies formed, they created a complex web of gravitationally bound structures connected by vast filaments of dark matter. The voids in this model are simply the regions between these filaments where there is little matter. The voids are not the result of any force actively erasing matter, but rather the natural outcome of the formation of the cosmic web itself. This theory suggests that the voids are an inherent part of the large-scale structure of the universe. They are not empty space in the sense that nothing exists within them, but rather regions where galaxies and clusters of galaxies are sparse. The study of voids, therefore, can provide important clues about the processes that governed the formation of the universe's structure and the forces that shaped it. The impact of dark energy on void growth. While gravity and dark matter play significant roles in the formation of voids, dark energy, the mysterious force that is causing the accelerated expansion of the universe, also has a profound impact on the behavior of voids. Dark energy is thought to make up about 68% of the total energy content of the universe and is responsible for pushing galaxies apart, accelerating the expansion of the cosmos. Dark energy's effect on the growth of voids is particularly noticeable. As the universe expands, dark energy drives galaxies farther apart, causing the voids to grow larger. This accelerated expansion has led to the creation of larger and larger voids over time, as the galaxies that once filled these regions continue to move away from each other. In this sense, dark energy acts as a catalyst for the growth of cosmic voids, increasing their size and stretching the already existing empty regions. The relationship between dark energy and void growth is an important area of study, as it can help scientists understand the role of dark energy in the overall evolution of the universe. By observing how voids expand and change over time, astronomers can gain insights into the properties of dark energy and how it influences the large-scale structure of the cosmos. The growth of voids is, in many ways, a reflection of the broader dynamics of the universe, where dark energy continues to drive the accelerated expansion of space itself. The role of cosmic inflation in voids. The theory of cosmic inflation, which proposes that the universe expanded exponentially in the first moments after the Big Bang, also provides an important framework for understanding the formation of voids. During inflation, the universe grew from a subatomic size to nearly its current size in an incredibly short period of time. This rapid expansion caused small fluctuations in the density of matter, which eventually led to the formation of galaxies, clusters, and voids. According to the inflationary model, the density fluctuations in the early universe were responsible for creating the large-scale structure we see today, including the voids. The regions where matter was less dense during inflation eventually became the cosmic voids we observe. These early fluctuations set the stage for the formation of the cosmic web, and the voids are a direct consequence of these initial conditions. Inflationary theory also helps explain why voids are so large. The rapid expansion of the universe during inflation stretched out these density fluctuations, allowing them to grow into vast empty regions. Over time, as the universe continued to expand, these voids grew larger and more pronounced, becoming a key feature of the universe's large-scale structure. Speculative theories, voids and parallel universes. While the mainstream scientific theories of cosmic void formation are rooted in the observable properties of the universe, there are also more speculative ideas that suggest that voids may be linked to parallel universes or other dimensions. Some researchers have proposed that the voids could be evidence of bubbles in space-time that lead to the formation of other universes in a multiverse scenario. According to this hypothesis, our universe could be one of many that exist within a larger, multidimensional space. These parallel universe theories suggest that the voids may not be truly empty, but instead could represent boundaries or regions where other universes may exist. While these ideas are speculative and lack direct evidence, they highlight the profound mysteries that still surround cosmic voids and the universe at large. If these theories prove true, the discovery of cosmic voids could represent not just a window into the large-scale structure of our universe, but also a potential gateway to understanding the existence of parallel universes or higher dimensional spaces. Voids as a window into the universe's future. In addition to their role in the evolution of the universe, cosmic voids may also provide clues about the future of our cosmos. As voids grow and expand, they offer a glimpse into the fate of the universe itself. The continued growth of voids, driven by dark energy, could be a precursor to the eventual fate of the universe. Some theories suggest that the accelerated expansion of the universe will continue indefinitely, leading to a future where galaxies are separated by increasingly vast voids. This scenario, known as the Big Freeze, suggests that the universe will continue to expand until all matter is spread thin, leaving behind a dark, cold, and empty cosmos. In this sense, cosmic voids may serve as a cosmic time capsule, revealing not only the history of the universe, but also its potential future. The study of voids, therefore, is not just about understanding the present structure of the universe. It is also about gaining insights into its ultimate fate and the forces that will shape its distant future. One of the most perplexing and essential forces in the universe, dark energy, is tied closely to the nature and expansion of cosmic voids. While the concept of dark energy has been around for only a few decades, it has become one of the most influential factors in shaping the structure and evolution of the universe. Dark energy is responsible for the accelerated expansion of space itself, driving galaxies farther apart and influencing the growth of voids in a way that was once unimaginable. In this chapter, we will explore the role of dark energy in the formation and evolution of cosmic voids. We'll examine how this mysterious force contributes to the growth of voids, how it affects the overall dynamics of the universe, and what its presence in voids means for our understanding of the cosmos. By the end of this chapter, we will see how dark energy, far from being an abstract concept, plays a tangible role in the very fabric of space-time and the creation of vast empty regions between galaxies. What is dark energy? Before we can explore its role in cosmic voids, we need to define what dark energy is. In the simplest terms, dark energy is a mysterious form of energy that makes up about 68% of the universe. Unlike ordinary matter or radiation, dark energy does not emit, absorb, or reflect light, making it undetectable by traditional methods of observation. It is invisible to telescopes, and its effects can only be inferred from its influence on the universe's large-scale behavior. Dark energy was first introduced in the late 1990s as a result of observations made by two independent teams of astronomers who were studying the rate of expansion of the universe. They found that the expansion of the universe was not slowing down, as had been expected due to the gravitational pull of matter, but was instead accelerating. This unexpected discovery led to the realization that a mysterious force must be at work, pushing galaxies apart at an increasing rate. The name dark energy was coined to describe this unseen force that seemed to counteract the attractive force of gravity. While we know that dark energy exists, we still don't fully understand what it is. There are several hypotheses about the nature of dark energy, including the idea that it is a form of vacuum energy inherent to space itself, or that it could be a property of the fabric of space-time described by Einstein's general relativity. Regardless of its exact nature, the influence of dark energy is undeniable. It is the driving force behind the accelerated expansion of the universe. Dark energy's impact on the expansion of the universe. To understand the role of dark energy in cosmic voids, we must first consider its impact on the universe as a whole. In the early devoid universe, shortly after the Big Bang, the universe was expanding rapidly, driven by the release of energy during the explosion. For the first few billion years, the expansion of the universe was slowed by the gravitational pull of matter, both visible matter, like galaxies and stars, and dark matter, which makes up most of the mass in the universe. However, at some point in the universe's history, the expansion began to accelerate rather than slow down. This acceleration was due to the influence of dark energy, which counteracts the force of gravity and pushes galaxies farther apart. The acceleration of the universe's expansion has been ongoing for the past few billion years and continues to increase as dark energy remains the dominant force in the cosmos. The discovery of the universe's accelerated expansion was one of the most significant breakthroughs in modern cosmology, fundamentally changing our understanding of the universe's evolution. The fact that the universe is expanding at an ever-increasing rate suggests that dark energy is not only present, but it is becoming more powerful as the universe grows. This has profound implications for the future of the cosmos and, as we will explore, for the growth and evolution of cosmic voids. The relationship between dark energy and cosmic voids. Now that we understand the nature of dark energy, we can begin to explore its role in the formation and growth of cosmic voids. As mentioned earlier, cosmic voids are regions of space where galaxies are sparse or completely absent. These voids exist within the cosmic web, the large-scale structure of the universe, which is made up of galaxies, galaxy clusters, and vast stretches of empty space. The existence of voids is a direct consequence of the universe's expansion. As the universe grows, matter is pulled into the dense regions of galaxies and clusters, leaving vast regions of space empty. This process is influenced by gravity, which pulls matter toward the densest regions of the cosmic web, and dark energy, which pushes galaxies apart and accelerates the expansion of space. Dark energy plays a crucial role in the growth of these voids. As the universe continues to expand, dark energy causes the voids to grow larger, pushing galaxies farther apart and increasing the size of the empty regions between them. In this sense, dark energy acts as a stretching force, pulling galaxies and clusters apart and allowing the voids to expand. The growth of voids over time. The role of dark energy in the growth of voids is a key aspect of our understanding of the universe's future. The voids that exist today are the product of billions of years of cosmic evolution, shaped by the forces of gravity and dark energy. As the universe continues to expand, the voids will grow even larger, and the galaxies within them will move farther apart. This process of void growth is driven by the accelerated expansion of the universe, which is fueled by dark energy. The growth of voids is an ongoing process, and scientists predict that as the universe continues to expand, the voids will become even more pronounced. This expansion will create larger and larger gaps between galaxies, and the filaments of the cosmic web will stretch further apart. Over time, the voids could grow to the point where the galaxies in them are no longer gravitationally bound to any other structure, effectively becoming isolated islands in the vastness of space. In the distant future, the expansion of the voids, driven by dark energy, could lead to a universe that is largely empty. This scenario, known as the Big Freeze, suggests that the continued acceleration of cosmic expansion will eventually cause galaxies to move beyond the observable universe, leaving only isolated, dark, and cold regions in the cosmos. The Big Freeze is one of the proposed end scenarios for the universe, and the growth of voids plays a crucial role in this potential future. Dark energy's influence on galactic motion. The presence of dark energy also has an impact on the motion of galaxies within voids. In areas of the universe where galaxies are sparsely distributed, such as within the voids, dark energy causes galaxies to move at a different rate compared to galaxies in denser regions of the universe. This difference in motion is due to the fact that voids have lower gravitational influences compared to the dense regions of galaxy clusters, and the expansion driven by dark energy causes galaxies within the voids to accelerate outward. Scientists have studied the motion of galaxies in and around voids to better understand the effects of dark energy. Observations show that galaxies in voids tend to move more slowly than galaxies in denser regions. This is because the gravitational pull of nearby galaxies is weaker in the voids, and the effect of dark energy dominates. As a result, galaxies within voids experience the full impact of the accelerated expansion, leading to faster motion and increasing distances between galaxies. The motion of galaxies within voids also provides valuable insights into the overall structure of the universe. By observing how galaxies move and interact with one another in different regions of the universe, scientists can test models of dark energy and refine their understanding of how it influences the large-scale behavior of the cosmos. The accelerating growth of voids, a window into dark energy. One of the most fascinating aspects of cosmic voids is that they provide a unique opportunity to study dark energy. While the effects of dark energy are not directly observable, the way it influences the growth of voids offers a window into its behavior. By studying how voids expand and how galaxies move within them, scientists can gather valuable data on the properties of dark energy and its impact on the universe. The growth of voids is also a direct reflection of the accelerated expansion of the universe. By measuring the rate at which voids grow and the distances between galaxies in voids, scientists can refine their understanding of the expansion and gain more insight into the nature of dark energy. This research is ongoing, and as new data is collected, our understanding of dark energy will continue to evolve. In the future, the continued study of voids and their relationship with dark energy may help scientists answer some of the most fundamental questions about the universe. How does dark energy interact with other forces in the universe? What are its properties, and how can we measure its effects more precisely? These are just some of the questions that the study of cosmic voids can help address, providing us with deeper insights into the forces that shape our universe. Voids and the fate of the universe. As we explore the role of dark energy in the cosmic void, we are also confronted with the broader implications for the future of the universe. The accelerated expansion of the universe driven by dark energy suggests that the cosmos will continue to stretch indefinitely. The voids, as regions of low-density space, will continue to expand as dark energy exerts its influence, and the distances between galaxies will only grow larger over time. This expansion could eventually lead to the end of the universe as we know it. As galaxies move farther apart, they will become increasingly isolated, and the universe will become darker and colder. This scenario, known as the Big Freeze, is one of the proposed end states for the universe, and it is directly tied to the growth of cosmic voids. The Big Freeze is just one possible future for the universe, but it highlights the critical role that dark energy plays in shaping the cosmos. By studying how dark energy affects the growth of voids, scientists can gain insights into the fate of the universe and what might happen as the expansion continues to accelerate. Cosmic voids, vast and seemingly empty regions of space, have long been the subject of fascination and scientific inquiry. While much of the focus on voids has revolved around understanding their formation, growth, and impact on the cosmic web, there's a more unsettling and speculative hypothesis that raises questions far beyond the scope of traditional astrophysics. Could cosmic voids be more than just empty spaces between galaxies? Could they be evidence of something far more profound and mysterious, something beyond our current understanding of space-time and the fundamental forces that govern the universe? In this chapter, we will explore the most disturbing and speculative hypothesis about cosmic voids, that they may be the result of a larger unknown force or structure that we have yet to detect. This idea challenges the very nature of reality itself, suggesting that the voids may not be empty at all, but instead represent the boundaries or traces of something far more exotic and far-reaching. From the possibility of parallel universes to the existence of higher dimensions, we will examine the theories that propose voids as a window into a hidden, unknown aspect of the cosmos. The void as a cosmic boundary. One of the more disturbing and fascinating theories about the cosmic void is that it could represent a boundary or edge to the known universe. In a universe that is constantly expanding, the idea that voids could be the result of an external structure or influence is a provocative one. What if these voids are not simply regions where matter is absent, but are in fact regions where something else, something beyond our current understanding, exists? Could cosmic voids mark the edges of a higher dimensional space, or perhaps even the boundaries between parallel universes? The concept of a cosmic boundary suggests that voids are not simply empty space, but rather areas where space itself begins to break down or transition into something else. This idea ties into certain speculative models of the universe, including the multiverse theory, the idea that our universe is one of many that exist within a larger, multidimensional space. In this model, each universe may be separated by vast voids, with the voids themselves acting as the boundary between universes or as regions where different dimensions interact. If voids are the result of such a boundary, it raises profound questions about the true nature of reality. The existence of parallel universes or higher dimensional spaces would fundamentally alter our understanding of space, time, and the very fabric of the cosmos. It would suggest that the universe we observe is only one of many, and that what we perceive as empty space may in fact be a window into a hidden and largely inaccessible realm. Voids as evidence of higher dimensions. One of the most intriguing and speculative hypotheses about cosmic voids involves the possibility that they are the result of higher dimensions of space. According to theories like string theory and M theory, the universe may have more than the 3 dimensions of space that we experience in our everyday lives. These theories propose that there may be additional dimensions beyond the familiar 3, and that the forces of gravity and other fundamental forces might interact in ways we have yet to understand. If these extra dimensions exist, they could be responsible for the formation of voids. According to this hypothesis, the voids might not be empty at all, but rather regions where the effects of higher dimensions are felt more strongly. These regions could be areas where the structure of space-time is fundamentally altered by the presence of additional dimensions. As a result, the voids we observe could represent windows into higher dimensional space, where the laws of physics as we know them break down or behave differently. In this view, cosmic voids would not just be large gaps between galaxies, they would be zones of transition between the familiar 3-dimensional world and the higher dimensional, spaces that might underlie our universe. This idea is both thrilling and deeply unsettling, as it challenges our basic understanding of the nature of space itself. If voids are indeed linked to higher dimensions, it could open up an entirely new realm of physics, one that is currently beyond our grasp. The multiverse hypothesis, voids as portals between universes. Another equally fascinating and unsettling idea is that cosmic voids may be connected to the multiverse, the idea that our universe is just one of many in a larger, possibly infinite collection of universes. According to this theory, our universe is not unique, and there may be an infinite number of parallel universes, each with its own set of physical laws and constants. These universes could exist in the same space, but be separated by vast voids, regions where the laws of physics differ or where the matter of one universe does not interact with that of another. In the context of the multiverse hypothesis, cosmic voids would not be mere empty regions between galaxies, but rather boundaries or barriers that separate different universes. The voids could be the result of the interactions between universes that exist in a higher dimensional space, where the boundaries between universes are not physical, but are marked by these vast, empty expanses. The voids might even be places where universes can leak into one another, or where interactions between them can cause the formation of new cosmic structures. This idea leads to a provocative question. Could we be living in a universe that is part of a vast multiverse, where voids represent the limits or transitions between different realms of existence? While this hypothesis remains speculative, it taps into some of the most profound and unexplained aspects of modern cosmology. The concept of the multiverse challenges everything we know about the universe, suggesting that the cosmic voids are not just empty spaces, but potentially the very edges of the greater reality. The voids as evidence of an unknown force. While theories about higher dimensions and parallel universes are speculative, they are not entirely out of the realm of possibility. However, another hypothesis that has gained traction in recent years is that the voids are evidence of some unknown force, a force that operates beyond our current understanding of gravity, dark energy, and other known forces in the universe. This idea proposes that voids may be the result of a phenomenon or interaction that is not accounted for by our existing theories of physics. One possibility is that the voids could be linked to the effects of quantum mechanics on the large scale. Quantum mechanics, the branch of physics that deals with subatomic particles and their interactions, has long been known to behave in ways that are counterintuitive and strange. Some researchers have suggested that the principles of quantum mechanics could extend to the large-scale structure of the universe in ways we have yet to fully understand. If this is the case, the voids could be the result of some quantum mechanical effect that is not yet detectable by our current instruments. Alternatively, the voids might represent the influence of an unknown force that operates in the space between galaxies. This force could be a new fundamental interaction that we have yet to detect, something that modifies the behavior of galaxies and their distribution across the universe. If this force exists, it could account for the apparent emptiness of the voids and the patterns of galactic motion that we observe. Voids and the fate of the universe. The speculation surrounding the role of voids in the universe extends beyond their mere existence. Some theories suggest that voids could be linked to the ultimate fate of the universe. For example, the concept of vacuum decay, the idea that the universe could undergo a phase transition into a lower energy state, has been proposed as a possible explanation for the eventual collapse or death of the universe. In this scenario, the voids could play a critical role in the process, acting as the regions where this transition begins. This idea links the voids to the eventual end of the universe, suggesting that the empty spaces between galaxies could be a sign of a much larger cosmic-scale event. If voids are indeed related to some unknown force or structure that affects the entire universe, their continued growth could signal that the universe is undergoing a fundamental shift that will eventually lead to its collapse or transformation. Some versions of this hypothesis suggest that as the voids continue to grow, they will eventually cause the universe to reach a state where matter and energy are so spread out that the cosmos becomes cold and dark. This concept, known as the Big Freeze, is one possible end for the universe, where the accelerating expansion driven by dark energy will continue until galaxies and stars are so far apart that they can no longer interact. In this scenario, voids will become the dominant feature of the universe, representing the final state of cosmic entropy. Philosophical implications. The void as the unknown. Beyond the scientific theories and hypotheses, the concept of cosmic voids also carries profound philosophical implications. The void represents the unknown, the spaces that are seemingly empty but may hold secrets that challenge our understanding of reality. It reminds us that there are still vast regions of the universe that are beyond our comprehension, places where the laws of physics and the structure of space-time may operate in ways that we cannot yet detect. The idea that voids might be evidence of an unknown force or an entirely new aspect of the cosmos forces us to confront the limitations of our current knowledge. It challenges us to consider that the universe is far stranger and more complex than we can imagine, and that there may be forces at play in the voids that we are not yet equipped to understand. This philosophical exploration invites us to embrace the mystery and uncertainty of the universe, knowing that the answers we seek may be hidden just beyond the veil of what we can observe. The discovery and study of cosmic voids have far-reaching implications for our understanding of the universe. These vast empty regions of space are not simply voids in the sense of being empty. Rather, they are integral components of the large-scale structure of the universe. As we continue to explore the true nature of these cosmic gaps, we must reconsider the foundational principles that guide our understanding of space, time, and the forces that shape the universe. The study of cosmic voids challenges established ideas about cosmology, structure formation, and even the fundamental laws of physics. In this chapter, we will examine the broader implications of cosmic voids on our understanding of the universe. What do these empty regions tell us about the fundamental forces that govern the cosmos? How do voids influence the way galaxies form, move, and interact? And what do they reveal about the future of the universe? These questions, though speculative, are central to the ongoing exploration of voids and their place within the larger framework of cosmic structure. Voids as a window into the universe's large-scale structure. The discovery of cosmic voids has revolutionized the way we think about the structure of the universe. Prior to the identification of voids, it was assumed that the universe was uniformly filled with galaxies and other cosmic matter. The existence of vast regions of low-density space, however, challenges this assumption and forces scientists to rethink the fundamental structure of the cosmos. Cosmic voids are not random gaps in the universe. They are part of the cosmic web, a vast network of interconnected galaxies and galaxy clusters that form the large-scale structure of the universe. The cosmic web is a result of gravitational forces that pull matter together, forming dense regions of galaxies while leaving vast expanses of empty space between them. Voids are integral components of this web, and their study has provided valuable insights into the way the universe has evolved over billions of years. The identification of voids has led to a more nuanced understanding of how galaxies and other cosmic structures are distributed across the universe. Far from being evenly spread out, galaxies tend to cluster together in filaments, which form the spines of the cosmic web. Between these filaments lie the voids, vast regions that are not completely empty, but contain far fewer galaxies and other matter. Understanding the distribution of these voids is crucial for understanding the large-scale evolution of the universe. This realization has forced us to reconsider many of the assumptions we once held about the structure of the cosmos. The universe is not a uniform sea of matter, but a dynamic, evolving network of galaxies, clusters, and voids. This understanding has implications for everything from the formation of galaxies to the expansion of the universe itself. Voids and the evolution of the universe. The study of cosmic voids also has profound implications for our understanding of the evolution of the universe. The formation and growth of voids are closely tied to the expansion of the universe. As the universe continues to expand, the voids grow larger, and the galaxies and clusters at the edges of the voids move further apart. This ongoing expansion has been driven by the force of dark energy, a mysterious force that is causing the accelerated expansion of space. Dark energy, which makes up about 68% of the universe's total energy content, is responsible for pushing galaxies apart at an accelerating rate. This force is not just pushing galaxies farther away from each other, it is also causing the voids themselves to grow. As dark energy continues to exert its influence on the universe, the voids will continue to expand, increasing the distances between galaxies and clusters. This process is a key component of the Big Freeze scenario, where the universe will eventually become an increasingly cold, dark, and isolated place as galaxies move farther apart. The expansion of voids is a direct result of the cosmic acceleration caused by dark energy. As voids grow, the galaxies within them are increasingly isolated from one another. This process will continue for billions of years, with the expansion driven by dark energy continuing to outpace the gravitational forces that once held galaxies together. The study of voids allows us to observe this expansion in real time, providing a window into the universe's distant future. Understanding how voids evolve over time is essential for developing accurate models of cosmic expansion and the eventual fate of the universe. If dark energy continues to dominate the universe's expansion, voids will continue to grow and the cosmos will become more and more empty. This could have significant consequences for the formation of future galaxies, stars, and planetary systems, as the increasing isolation of galaxies will make it more difficult for new structures to form. Voids and the distribution of dark matter. Dark matter plays a crucial role in the formation and structure of the universe. Though dark matter cannot be directly observed, its presence is inferred from its gravitational effects on visible matter. Dark matter is thought to make up about 27% of the universe's total mass, and it is believed to be responsible for holding galaxies and galaxy clusters together. It is also thought to be concentrated in the cosmic filaments that connect galaxy clusters, while the voids are regions with less dark matter. The distribution of dark matter across the universe has a profound effect on the way galaxies and clusters form. In areas with a higher concentration of dark matter, galaxies tend to cluster together, forming large-scale structures like superclusters and galaxy groups. In contrast, voids are areas where dark matter is less abundant, leading to the sparse distribution of galaxies and other matter. This difference in dark matter density is what gives voids their characteristic low-density nature. The study of dark matter in relation to voids has provided valuable insights into the role of dark matter in the evolution of cosmic structure. By mapping the distribution of dark matter in the cosmic web, scientists have been able to develop more accurate models of how galaxies and clusters form and how they interact with one another. This research is ongoing, and new techniques such as gravitational lensing and weak gravitational lensing are allowing scientists to study dark matter in even greater detail. Understanding the distribution of dark matter in voids is crucial for refining our models of galaxy formation. As we continue to study the role of dark matter in the evolution of voids, we will gain a deeper understanding of how the universe has developed over time and how it will continue to evolve in the future. Voids and the role of gravity. Gravity is the fundamental force that shapes the structure of the universe, pulling matter together and causing the formation of galaxies, stars, and clusters. However, in the empty regions between galaxies and clusters, regions we call cosmic voids, gravity plays a very different role. In voids, gravity is weaker and the pull of matter is less concentrated, which leads to the relative emptiness of these regions. While gravity is still present in voids, its influence is less pronounced than in denser regions of the universe. The lack of significant gravitational pull means that the galaxies within voids move more slowly and experience less interaction with other galaxies. This difference in gravitational forces is one of the reasons why galaxies in voids tend to be more isolated than those in denser regions of the universe. In some cases, galaxies in voids can evolve in unique ways, unaffected by the gravitational influence of nearby galaxies. The relationship between gravity and the voids is an important area of study, as it helps scientists understand how galaxies form and evolve in different environments. By studying how gravity operates in voids, scientists can learn more about how matter behaves in regions with less density and how gravitational forces shape the universe on the largest scales. The future of void research and the universe's fate. The study of cosmic voids is still in its early stages, and much remains to be discovered about these vast empty regions. As new technologies and telescopes come online, we will be able to observe voids with greater precision and explore their role in the evolution of the universe. The continued study of voids will also provide valuable data about the behavior of dark energy, dark matter, and other forces that govern the universe. The future of void research is closely tied to the study of the universe's ultimate fate. As dark energy continues to drive the accelerated expansion of the cosmos, the voids will grow larger and galaxies will become more isolated. This process will eventually lead to the Big Freeze, where the universe becomes dark, cold, and empty. The growth of voids and the isolation of galaxies will be a key feature of this eventual scenario. While the future of the universe remains uncertain, the study of cosmic voids will continue to be a crucial part of understanding how the cosmos has evolved and what its eventual fate will be. By studying the expansion of voids and the forces that shape them, we can gain deeper insights into the ultimate destiny of the universe and the role that dark energy and dark matter will play in that future. Conclusion: the universe's hidden complexity. The discovery of cosmic voids has forever altered our understanding of the universe. These vast empty regions are not just the gaps between galaxies, but integral components of the cosmic web that reveal the true complexity of space and time. The study of voids has challenged traditional views of the universe, forcing us to reconsider our understanding of cosmic structure, dark energy, dark matter, and gravity. While much has been learned about cosmic voids, much more remains to be discovered. The relationship between voids, dark energy, and the expansion of the universe continues to be one of the most exciting and perplexing areas of research in modern cosmology. As we look to the future, the study of voids will play a key role in our ongoing quest to understand the nature of the universe, its ultimate fate, and the forces that drive its evolution. As we continue to explore the empty regions of space, we are reminded that there is always more to discover in the vast, uncharted territory of the cosmos. The mysteries of the void are far from solved, and they will continue to captivate and challenge scientists for years to come. As we delve deeper into the mysteries of cosmic voids, one of the most thought-provoking questions arises: what lies beyond the cosmic void? While the voids themselves are vast, empty spaces in the fabric of the universe, the question of what exists beyond them stretches the boundaries of our understanding. Could these empty regions mark the boundary of our universe, or do they provide a glimpse into dimensions beyond our current perception of reality? Could there be more to the voids than mere emptiness, something hidden in the unseen corners of space and time, beyond the reach of current observational tools? In this chapter, we will explore some of the most speculative and intriguing ideas about what lies beyond the cosmic void. From the possibility of higher dimensional spaces to the notion that voids might serve as portals to parallel universes, these hypotheses challenge our understanding of space-time and offer fascinating possibilities for the future of cosmology. In many ways, the cosmic voids are not just empty spaces, but potential windows into something far larger and more mysterious than we can imagine. The cosmic void as a gateway to hidden realms. The first idea we explore is the possibility that cosmic voids might be more than just large regions of low-density space. Instead, they might represent gateways to hidden realms, regions beyond the observable universe, or even dimensions that are inaccessible to us. The very emptiness of the voids might suggest that they are not devoid of substance, but rather represent the space between what we know and what lies beyond. These realms could be part of a larger, unknown structure of the universe, potentially involving extra dimensions or parallel universes. This hypothesis is rooted in speculative physics, particularly string theory and M-theory, which suggest the existence of more than the three spatial dimensions that we experience. According to these theories, the universe could contain additional spatial dimensions that are compactified, meaning they are curled up and inaccessible to us on the human scale. Some physicists propose that the cosmic voids could be regions where the effects of these higher dimensions become apparent, either as a result of the way space-time is warped or as regions where the edges of other dimensions might intersect with our own. If cosmic voids are indeed connected to higher dimensional spaces, they would represent the boundaries or transitions between different layers of reality. Rather than being empty, these voids could be zones of transition, spaces where matter and energy behave in ways that are fundamentally different from the familiar three-dimensional universe. These regions could contain information about the true nature of space-time, hidden forces, and dimensions that are still beyond our current understanding. If future research proves this theory, it could open entirely new areas of physics, providing insights into the fundamental structure of the universe and the multidimensional space in which it exists. Voids and the multiverse, portals to parallel universes. One of the most fascinating ideas about what lies beyond the cosmic void is the multiverse hypothesis. According to this theory, our universe is not the only universe in existence. Instead, there could be an infinite number of parallel universes, each with its own set of physical laws, constants, and properties. These universes could exist in the same space-time continuum as our own, separated by vast unimaginable distances or even higher dimensions that we are unable to detect. In this model, cosmic voids could act as portals or barriers between different universes. They could represent the boundaries between regions of space-time where different universes interact or overlap. Just as voids separate the filaments of galaxies in the cosmic web, they could also act as the physical separation between parallel universes in a much larger multiverse. This idea suggests that the voids are not merely empty, but are in fact connected to something far larger and more complex than our universe. These voids may not represent nothingness, but could be seen as the spaces between the universes in a much larger, multi-dimensional reality. The multiverse hypothesis is still highly speculative and remains a topic of intense debate among physicists and cosmologists. While the idea of multiple universes is intriguing, it is difficult to test or prove with current technology. However, if voids do serve as links between different universes, they could provide a glimpse into the fundamental nature of reality itself. If future observations reveal unexpected patterns or anomalies in the voids, it could suggest that our universe is just one of many, and that the voids are the spaces where these universes interact. Voids in the nature of space-time, a window into the unknown. Another speculative theory about the voids is that they are tied to the nature of space-time itself. According to the theory of general relativity, space-time is a four-dimensional fabric that can be warped and stretched by the presence of matter and energy. Massive objects like stars and black holes bend space-time around them, creating the effects of gravity that we observe. The voids, however, represent regions where this warping of space-time is minimal, allowing space to remain relatively flat and unperturbed by gravitational forces. But what if the voids are not just areas of minimal curvature in the fabric of space-time? What if they are regions where space-time itself behaves differently, where the fundamental laws of physics are altered, or where the nature of time and space is fundamentally altered by some unseen force? If space-time is truly a dynamic, flexible structure, it could be that the voids represent areas where this flexibility is more pronounced. These regions could be places where space and time intersect with other dimensions or higher planes of existence, where the rules of physics as we understand them break down. Some researchers have even suggested that voids might be the result of quantum fluctuations, tiny random changes in energy that occur in the vacuum of space. According to this hypothesis, voids could represent regions where the vacuum state of space is less stable, leading to fluctuations that cause the formation of empty gaps between galaxies. These fluctuations could provide clues about the fundamental nature of the universe and how space-time behaves at its most fundamental level. Understanding these fluctuations could lead to breakthroughs in quantum gravity and our understanding of how the forces of gravity and quantum mechanics interact. The void as a precursor to the end of the universe. While the idea of voids being linked to higher dimensions or parallel universes is speculative, the notion that voids could play a role in the end of the universe is both thought-provoking and unsettling. As we've explored in previous chapters, voids are expanding as the universe itself continues to grow. This accelerated expansion, driven by dark energy, is causing the voids to become larger and larger over time. In the distant future, this expansion could result in a big freeze, a scenario in which the universe becomes increasingly cold, dark, and isolated. The big freeze suggests that the ongoing growth of the voids could lead to a state where the universe is no longer able to sustain the formation of stars or galaxies. As galaxies move farther apart and the matter within the universe becomes more spread out, the universe will become a barren, dark place. The voids, which are already vast, will continue to expand, and the space between galaxies will become so great that any interaction between cosmic structures will become impossible. In this scenario, the voids are not just empty spaces, they are the harbingers of the universe's eventual demise. The continuing growth of the voids, driven by dark energy, will be one of the key features of the universe's end. The voids will continue to expand as the universe stretches into an ever greater void, a cold, lifeless cosmos where galaxies are scattered across an infinite expanse of emptiness. The concept of voids as the precursors to the Big Freeze raises the disturbing thought that these regions of space are not only areas of emptiness, but are also the places where the universe's ultimate fate will unfold. Exploring the void, the search for new understanding. As we continue to explore the mysteries of cosmic voids, we must keep in mind that these vast regions of space are not simply gaps in the universe. They are windows into the unknown, places where the conventional rules of space and time break down and where new ideas about the nature of the universe can emerge. Whether voids are linked to higher dimensions, parallel universes, or the eventual fate of the cosmos, they are a reminder that there is still much we do not know about the universe. The study of cosmic voids is still in its early stages, and future research will likely reveal even more surprising and profound insights. Advances in telescope technology, gravitational wave detection, and quantum simulations will provide us with new ways to observe and study voids. By examining the size, shape, and behavior of voids, we will be able to test our hypotheses about the universe's fundamental nature. The more we learn, the more we will uncover the hidden layers of reality that exist beyond our current perception. Whether we are studying the cosmic web, exploring the role of dark energy, or speculating about parallel universes, the voids offer a unique opportunity to explore the deepest questions of existence. They are not just empty spaces, they are the key to understanding the true structure of the universe and the forces that govern it. As we conclude our exploration of cosmic voids, we are left with a profound sense of wonder and intrigue. What we have uncovered so far is just the tip of the iceberg when it comes to understanding the vast, empty regions that dot the universe. While cosmic voids may seem like nothing more than empty spaces between galaxies, they are anything but insignificant. These voids challenge our understanding of the universe's structure, the fundamental forces that govern it, and even the very nature of space-time itself. From the formation and growth of voids to their role in shaping the large-scale structure of the cosmos, voids are central to our understanding of how the universe has evolved over time. But even as we piece together the puzzle of these vast empty regions, We find that the answers they provide are often just the beginning of new questions. The voids force us to confront the limits of our knowledge and challenge our assumptions about the nature of space, time, and the forces that govern the universe. And it is in these challenges that the true excitement of cosmology lies, the thrill of discovering that there is always more to uncover in the vastness of the cosmos. The significance of cosmic voids. Cosmic voids are not merely gaps in the universe. They are fundamental features of the large-scale structure of the cosmos, revealing the complex distribution of matter and energy across vast distances. The discovery of voids has fundamentally reshaped our understanding of the universe, forcing scientists to rethink the way galaxies and other cosmic structures are distributed. Rather than being uniformly spread out across space, galaxies form into clusters and filaments, leaving behind vast empty spaces that are not devoid of interest, but instead rich with the potential for new discoveries. These voids serve as an important reminder that the universe is far more complex than we once imagined. They are not empty in the sense of being meaningless or insignificant, but are instead integral to the fabric of the universe. By studying voids, we gain insights into the forces that shape the cosmos, from the early moments of the Big Bang to the ongoing expansion driven by dark energy. The study of voids challenges the simplistic view of the universe as a uniform, static entity, and instead reveals it to be a dynamic, ever-evolving system of galaxies, dark matter, and unseen forces. As we continue to explore the voids, we are forced to confront the fundamental questions of cosmology. Why do voids exist? What forces shape their growth? And what do they tell us about the future of the universe? These questions are not easily answered, but they are central to the pursuit of knowledge in cosmology. The mysteries of the voids are a reminder that the universe is still full of unknowns, and that the pursuit of answers is an ongoing journey that will span generations. The role of dark energy in void expansion. One of the most exciting and perplexing aspects of the study of voids is the role of dark energy, the mysterious force responsible for the accelerated expansion of the universe. The presence of dark energy is most apparent in the way voids grow over time. As the universe expands, dark energy continues to push galaxies farther apart, causing the voids to expand as well. This phenomenon will continue for billions of years, eventually leading to a universe where galaxies are isolated in vast stretches of empty space. The growth of cosmic voids, driven by dark energy, is one of the most profound implications of our current understanding of the universe's future. It suggests that the universe is not just expanding in a simple, uniform way, but that different regions of space will evolve at different rates depending on the density of matter and the influence of dark energy. This dynamic, ongoing expansion is a central feature of modern cosmology and is a key area of research for scientists studying the large-scale structure of the universe. Dark energy's role in the growth of voids is not only significant for understanding the present state of the universe, but also for predicting its future. The accelerated expansion driven by dark energy suggests that the universe will continue to expand indefinitely, with the voids growing ever larger. This will eventually lead to a state where galaxies are no longer able to interact with one another, and the universe will become increasingly cold, dark, and empty, a scenario known as the Big Freeze. The growth of voids, in this sense, is a sign of the universe's ultimate fate, as dark energy drives the cosmos toward an ever-increasing state of isolation. The enigmatic nature of voids. A window into the unknown. Perhaps the most profound aspect of cosmic voids is their enigmatic nature. These vast regions of space are not simply empty, they are a fundamental part of the cosmic puzzle. As we study the voids, we are not just studying empty regions of space, but rather trying to understand the deeper, unseen forces that govern the universe. What makes voids so fascinating is the possibility that they may be hiding something far beyond our current understanding, something we have yet to discover. Could the voids be the result of a larger, unknown force or phenomenon that we are not yet capable of detecting? Could they be related to higher dimensional spaces, parallel universes, or even quantum fluctuations? These speculative ideas are at the cutting edge of modern physics and cosmology, and they suggest that the voids are not simply empty regions, but may be the key to unlocking some of the universe's deepest mysteries. The study of voids offers a unique opportunity to explore the boundaries of our knowledge and to push the limits of our understanding. They are not just gaps in space, they are clues to the fundamental nature of the universe, offering a window into the unknown. The voids represent the edges of our comprehension, and they challenge us to reconsider what we know about the fabric of reality itself. The void and the future of the universe. Looking toward the future, cosmic voids will continue to play a central role in shaping our understanding of the universe. As our observational technology improves, we will be able to study voids with greater precision, gaining new insights into the forces that drive their expansion and growth. Instruments like the James Webb Space Telescope and future gravitational wave observatories will provide more data on the structure of voids, allowing us to study them in more detail than ever before. One of the most exciting possibilities for the future is that the study of voids could provide valuable clues about the fate of the universe. As voids grow, driven by dark energy, they will reshape the cosmos in ways we are only beginning to understand. The eventual fate of the universe, whether it ends in a big freeze, a big crunch, or some other scenario, will be influenced by the ongoing growth of voids. Understanding the dynamics of these voids will allow us to predict how the universe will evolve in the far future and what that future might look like. The study of voids is also closely tied to the search for new physics. The existence of cosmic voids, the expansion of the universe, and the role of dark energy and dark matter all suggest that there are deeper, unseen forces at play in the cosmos. By studying voids, we may be able to uncover new laws of physics, new dimensions of space, and new understanding of how the universe works on the largest scales. The philosophy of the void. What does it mean for us? Beyond the scientific implications, the concept of the cosmic void also has philosophical significance. The void represents the unknown, the unexplored, and the mysterious. It forces us to confront the limits of our knowledge and our place in the universe. In a sense, the void is a metaphor for the vastness of existence itself, the infinite unknown that stretches out before us, waiting to be discovered. Philosophically, the void invites us to consider the nature of existence, the meaning of emptiness, and our role in the grand scheme of the universe. What does it mean to live in a universe that contains such vast emptiness? How does our understanding of the void shape our understanding of ourselves and our place in the cosmos? The study of voids forces us to look outward, to confront the enormity of the universe, and to recognize that there is always more to learn, more to discover, and more to explore. In this way, the cosmic void is a profound reminder that the universe is a mystery waiting to be solved. It is a symbol of the unknown, the questions that have yet to be answered, and the infinite possibilities that await us as we continue to search for meaning in the vastness of space. Conclusion. The endless mystery of the void. The study of cosmic voids is far from over. What we have learned so far has opened up new questions, and the voids continue to hold secrets that we are only beginning to understand. These vast, empty regions of space are not just gaps in the universe. They are a window into the fundamental nature of reality itself. As we continue to explore the voids, we will uncover new truths about the universe, the forces that govern it, and our place within it. While much remains unknown, the journey of discovery continues. The voids are not simply empty spaces, they are the key to understanding the universe's past, present, and future. They are a reminder that there is always more to explore, more to discover, and more to learn. The mysteries of the void are the mysteries of the universe itself, and the answers we seek may ultimately reveal the deepest truths about the cosmos.